Right, good morning, good afternoon, or good evening, whatever time you're watching this educational video. We will be discussing now about instantaneous acceleration. But before anything else, I want you to, support this channel if you like contents like this. Right, without further ado, let's have the North Stars of our instantaneous acceleration. We will agree that the symbol of our instantaneous acceleration will be A, then ins. It means instantaneous acceleration. So as we all know, acceleration is the change, it's the change in velocity, but this time since it's instantaneous acceleration at an instant or specific moment in time, just like instantaneous velocity at certain second. This time change in velocity at an instant or specific moment in time, we are dealing with instantaneous acceleration. And always remember this one, that the derivative of the velocity function, again, derivative of the velocity function, it equates our instantaneous acceleration. Another definition here, it's a change in velocity over a very small period. Okay, again and again, our instantaneous acceleration is the derivative of our velocity function. Okay, so I have here some word problem, but before that, please remember as well that if the problem involves position function, of course, before you will get the instantaneous acceleration, you have to get first the derivative of this position function. Okay, and after getting the derivative of the position function, of course, that will become the instantaneous velocity. And if you have calculated the derivative of position, and now it's the instantaneous velocity, the derivative of the instantaneous velocity will be our instantaneous acceleration. It's the derivative of velocity function. Again, please be careful or analyze the problem first if it gives you a position function or it gives you already the velocity function before you will calculate the instantaneous acceleration. So in this problem here, using instantaneous velocity function, so it's good. No need to do the derivative because the function gives us the velocity function or the derivative of the position. Okay, so again, the first derivative of the position, that's our velocity function here. So no need to get the derivative. All right. So where V is meter per second and T is seconds or S. Let's provide the average acceleration between 3 and 5 seconds and the instantaneous acceleration of the object at 4 seconds. So first, we will calculate first the average acceleration. To get the average acceleration, our formula, if you could still recall, it's the change in velocity over change in time. Change in velocity, we have V final minus V initial over T final minus T initial. Okay, so we will substitute directly to get the velocity at 3 seconds and 5 seconds to our velocity function. Okay, so we will just copy our velocity function here. Our velocity at 3 seconds. Okay, so T3 minus 2 T2 or squared plus 3. This is our function here provided in the problem. I just copied it. And then we will substitute 3 to every t variable here. So you have T3. So instead of writing t, get or put 3 as its value minus 2. And then you have t here. Replace it with 3 and then squared plus 3. 3, it's cube, right? So 3 times 3 times 3. That's 27 minus negative 2 times positive 3. That's negative. Oh, okay. So before you will multiply it, don't forget to square first 3. So 3 times 3, that's 9 plus 3. 27 negative 2 times negative 9, so 9, so it's 18 plus 3. Our answer is 27 plus 27 minus 18 plus 3. So you will have 12. Remember the unit of velocity, meter per second. This is the velocity at 3 seconds. So what about the velocity at 5 seconds? So velocity at 5 seconds, copy the given velocity function here. Put or replace t with 5, cube minus 2, 5, then squared plus 3. 5 times 5 times 5, it will give you 125. Then 2, 5 times 5, 25 plus 3. So you have 125, negative 2 times 25, that's negative 50 plus 3. And 125 minus 50 plus 3 will have 78 meter per second. So this is our velocity at 5 seconds. All right, so we have the value of our, of course, this is our initial velocity, and this will be our final velocity. So we will plug in our values here to our formula. So VF is equal to 78 meter per second minus VI. VI is 12 meter per second all over final time from 3 to 5. 5 is our final time, 5 seconds minus initial time, 3 seconds. Okay, so 78 minus 12, you'll have 66 meter per second. Then you have 5 minus 2 seconds, that's 2 seconds. And if you will divide it, you will have 33 meter per second squared. I will just rewrite the answer of our average velocity here. It's 33 meter per second squared. That's the average velocity. So now we're not yet done. We need to find the instantaneous acceleration at 4 seconds. Okay, and we have our velocity function here. And remember, the derivative of our velocity function, that's the function that we will be using in getting the instantaneous acceleration. So we need to get the derivative of our vt function here. Okay, so use the power rule, put 3 here, and then t, 3 minus 1 minus put 2 here, and then 2 t2 minus 1 plus 3, and since it's constant is always zeros, so we will just remove 0 there. Okay, so let's refine our answer. 3 t squared minus negative 2 times a negative 2 times positive 2, that's 4 t. 2 minus 1, it's 1, but we can simply remove 1. So our derivative of our velocity function is 3t squared minus 4t, and we will be using that one to get the instantaneous acceleration at 4 seconds. So the instantaneous acceleration, 4 seconds, or you can just write a with respect to time. So a at 4 seconds is 3t squared plus 4t. And let's substitute 4 to our time variable here. So 4 squared minus 4 and then 4. So 3, don't forget, 4 times 4, it's 16 minus 16. And then 16 times 3, I'll get 48 minus 16. And the answer is 32 meter per second squared. So this is our instantaneous acceleration at 4 seconds. We have this given here, the position function. Let's say 3t raised to 4 minus 3t cubed plus 2 raised to t. Okay, if we have this position function here, 3t raised to 4 minus 3t cubed plus 2t. It's a position function. So therefore, we need to get the first derivative of it or the derivative of it to get the, velocity function or our velocity. So in that case, for example, I want you to get the average acceleration from 7 seconds to 9 seconds and then get the instantaneous acceleration at, let's say, 8 seconds, in between 7 and 9 seconds. Let's get the instant acceleration at 8 seconds. Again, we have a position function, and then we need to get the average acceleration and the instantaneous acceleration at 8 seconds. Let's do it. Since it's still position function, we need to get the derivative of it in order for us to get the velocity function. Let's go. X prime of t is equal to, I will write first the function so that we will be guided properly. So all we have to do is to put 4 here, 4, and then multiplied by 3, then t, 4 minus 1. Copy negative. Then, yeah, 3 times 3. T, 3 minus 1 plus 2. It's understood you have 1 here. Put that 1 in front of 2. And then t, 1 minus 1. Let's simplify. 4 times 3, 12. And then t, 4 minus 1, that's going to be 3. Okay. So, in this case, you will have negative 3 times negative 3, that's negative 9. Then t, 3 minus 1, it's 2. Plus 1 times 2, of course, that's 2. And then t, 1 minus 1 is 0. Remember, a variable raised to 0, it's equal to 1. So we can still refine our answer here. So 12t cubed minus 9t squared plus 2 times 1, of course, it it is equal to 2. So this is our velocity function. So we will be using this function to get the instantaneous acceleration, and the as well as the average acceleration. Let's begin first by finding the average acceleration. Our formula to get the average acceleration, it's the change in velocity, change in time. All right, let's get the average acceleration. Of course, we need to find the velocity at 7 seconds. And later, we will be getting the velocity at 9 seconds. So let's use this velocity function here, not this one. Okay, please be mindful. We get the derivative of our position function and we arrive to this derivative here. So please copy this one. The velocity at 7 seconds, 12t cubed minus 9t squared plus 2. So substitute 7 seconds to every t variable here. So 12, 7 cubed minus 9, 7 squared plus 2. 12, don't forget squared, not squared, but the cube of 7. It's 343 minus 9. Then squared of 7, it's 49 plus 2. We will multiply 12. 12 times 343, the answer is 4116. Negative times positive, it's negative. 9 times 49, the answer is 441 plus 2. And let's carefully plug in these figures here. 4116 minus 441 plus 2. The answer is 2677 meter per second. This is our velocity at 7 seconds. What about velocity at 9 seconds? Let's do it real quick. 12t cubed minus 9t squared plus 2. Let's substitute 9 to our t variable. 9 and then 9 squared plus 2. 12, don't forget, 9 times 9 times 9, it's 729 minus 9, then the squared of 9 is 81 plus 2. So 729 times 12 will get 8748. Then negative times positive, negative 9 times 8, 1. The answer is 729 plus 2. Let's plug in these figures carefully. 8748 minus 729 plus 2. You'll have 8,021 meter per second. So this is our final velocity. This is our initial time. 9 seconds is final time. So therefore, it's our final velocity, initial velocity. Let's plug in these values to our average acceleration formula. Okay. So BF minus VI, TF minus TI. Your VF, final velocity here, it's 8,021 meter per second minus initial 2677 meter per second all over final time 9 seconds minus 7 seconds. I will just erase this stuff here. Let's continue. So 821 minus 2677. The answer is 5344 unit meter per second. All over 9 minus 7, 2 seconds. And we will divide it by 2. So the answer will be 2672 meter per second squared as the average velocity between 7 to 9 seconds in our velocity function. Okay, we're not yet done. We need to determine our instantaneous velocity at 8 seconds. Now we need to find our instantaneous acceleration at 8 seconds. Okay, so this will be our velocity function here. So we need to get the derivative of that in order to get the instantaneous acceleration. Okay, so get the derivative or v prime of t to get the instantaneous acceleration. Use this, not this one. Okay, so let's get the derivative now. The v prime t is equivalent to our instantaneous acceleration. So instantaneous acceleration is equal to, let's copy first the velocity function. Let's get the derivative. So put it here, 3 times 12, then t3 minus 1. Okay, you have 2 times 9, and then t2 minus 1 plus 2. It's constant, so we can just remove it because it will become 0. 3 times 12, it's 36, and then t3 minus 1, it's 2. Then negative 2 times 9, you will have negative 918. Then t1, or we can just remove 1 here. So this is our, or this is a function that we will be using in getting the instantaneous acceleration. So let's get the instantaneous acceleration at 8 seconds. A-inst at 8 seconds. So let's plug in 8 to our derivative here. So that's A-inst is equal to 3060 squared minus 18t. So 36, and then replace t with 8, then squared 18, and then 8. So 8 times 8, it's 64, multiplied by 36 minus 18 times 8. So you will have 144. 36 times 64, you will have 2304 minus 144. Minus 144 will get 22160 meter per second squared, unit of acceleration. So this is the instantaneous acceleration at 8 seconds. Okay, I hope you got it right. Thank you for watching this educational video. Study this one for you to have an idea how to get the instantaneous acceleration if ever we have the position function given in the problem. Okay, thank you. And don't forget to support this channel. See you around until next time. Bye for now.